So good evening. Welcome to today's session. So in today's session, it is almost like the continuation of the last session what we discussed. We'll go through the problems or the situations we discussed in the last session. Now we'll try to solve each problem that we discussed. So actually today is almost a challenging session for me. So this is briefly. So these are the topics we are going to discuss in today's session. One is central limit theorem, and then we spend some time on the estimations related to sampling. So when we do the sampling, based on the sampling outcome, we'll try to estimate it for the population. So we'll spend 5 to 10 minutes on confidence intervals, followed by the errors that happens when we do testing of hypothesis. The next will take some cases where we'll try to see how to test the hypothesis or claim that is mentioned in the problem or situation. So this is what we are going to have. So first, so this is already what we discussed, a normal distribution, which helps us regularly in most of the applications that we are going to have. And so we need not remember this, just we need to understand that. So we have to convert normal distribution into standard normal distribution, and we have to use tables to find the corresponding probabilities. Now, so we'll go through the one simple topic, that is sampling distribution or distribution of samples. So here the idea is, suppose we had population as discussed in the earlier session. So to estimate or to understand the population, so that is how the population is behaving, what are the characteristics of the population. In such scenarios, what we are doing, because the population is very large, so what we are doing is we are going for sampling, right? So when we do sampling, what we are doing is we select samples of some size m. Then we do the analysis on the sample, that is we'll try to find mean of the sample. Then from this we'll try to estimate, or we'll try to understand the mean of the population. Right? This is what we discussed. But if you see in general also, when we try to do the sampling, when we particularly we try to implement this by using any of the tools available, maybe R or Python, whatever it is. So what we do is we fix the seed. Seed means that is we'll fix randomly. It has to select a sample with n equal to 100, n equal to 150, or whatever we select. Then it select random from the population. It select the sample consisting of n equal to 100. Then it will find whatever we are asking for, mean or variance, any measure we are looking for. In general, we won't stop with this. So because we need to understand the population, then we can ask again to go for another seed with the same n equal to 100. Yeah? That means another sample, and we'll ask the tool to calculate what is the mean, variance, or whatever we have. That means like this we do the sample one as shown here. Just a minute. So here suppose we took a sample of one sample. First sample we selected, second sample we selected, third sample we selected, like this. And suppose if we are considering mean, only mean, right, and variance also, we can find mean of the first sample, we can find mean of the second sample, we can find mean of the third sample, and so on, right? That means, so when we do the sampling here and we are selecting many various samples, then we, for each and every sample, we are finding mean in this case, and similarly we can find variance or whatever we are interested. Now what we do, because we had mean 1, mean 2, mean 3, and so on. Now let us define a random variable associated with it. That is, suppose if I take x bar as a random variable associated with the sampling distribution. Right? X bar is a random variable associated with these samples. Then if I take this, then what we can have is, we can have mean of first sample, mean of second sample, mean of third sample. Now if you remember, recall the discussion what we had with respect to random variable. Whenever a random variable is there, we can calculate its mean, right? Mean of the random variable. So that is here mu x bar. Similarly, we can have variance of the first sample, variance of the second sample, variance of the third sample, like this. So for this random variable whose variances are known, we can calculate, or we can say this is. Right? So random variable and corresponding mean is this, corresponding variance is this. Now here we will try to understand the relation between the sample outcomes and population parameters. Then it is observed, actually we are not doing the derivation. This is one of the important point to be noted. So I think for us the derivation is not helpful or useful or not necessary. But one observation is, this mu x bar is equal to mean of the random variable, mean of the population. Similarly, this mean of the sampling distribution is sigma square by. So I hope that is clear, right? So mu here, mu of sampling distribution is nothing but the same as mean of the population. Variance of the sampling distribution is given by this relation. I hope that we remember this. What is the sigma square? Sigma square is nothing but the variance related to the population. So this is one useful result we use frequently. So I hope that is clear, right? Next, if we go further, and this is one of the important theorem which helps us a lot. We do many things where central limit theorem allows us to do this. That is, now we know the process what we observed with respect to normal distribution, right? That is, if you remember something called as z equal to x, that is maybe not right here, x minus mu by sigma, if you remember, right? X minus mu by sigma, remember. So what is this x minus mu by sigma? This is nothing but we are converting a random variable which follows normal distribution into standard normal distribution. Right. That means if we know that it follows normal distribution, then we go for standard normal distribution. But that means now, particularly when we are dealing with population, and then when we are dealing with the sampling distribution, then there is no guarantee that we know the nature of the population. There is no clue whether it follows normal distribution or not. So what the central limit theorem says is, if irrespective of its nature, right, irrespective of its nature, whether it is following normal distribution or not, if the size of the sample is larger, then it follows normal distribution. Right? That means we have the freedom of using all these conversions with the help of central limit theorem. I hope that is clear. So what is the need or what is the use of central limit theorem. That is actually one important discussion. So in what way this central limit theorem helps us? So central limit theorem helps us to use normal distribution even there is no clue about the nature of the population, nature of the sampling distribution. So is there any other extra information that you want with respect to this? I hope that it is clear. Okay, right. So if it is clear, then we'll move to the next one. 1 minute. Okay, some questions. Yeah, 1 minute. Some questions are there. I just am going through. Yeah, we are using normal distribution only. Why we are calculating random variable is here because generally when we try to implement whatever the sampling whether we are taking is whether it is approximating the original population or not. That's why what we are doing, we are selecting a sample 1, selecting a sample 2, selecting a sample 3 like this. Then we will observe how it is behaving. So that's why we are doing this. So I think this question already I think I mentioned earlier also. So when we calculate the variance of sample, that is S square, generally we generate by S square is variance of the sample, sigma square is variance of the population. When we do or when we calculate, in general we know when we calculate variance our denominator contains m, but in case of the sampling variance, we instead of n we replace it by n minus 1. The reason is for the what they study is the theorems what the people tried, the scientists or the statisticians, they tried and found when instead of n, if you take n minus 1, it gives more accurate approximation. That is the reason they use n minus 1. I hope that point is clear. Generally we use n, but when we calculate variance with respect to samples, we replace n by n minus 1. That is one good point. Why we are calculating is because now we need to we are having the population just by taking one sample, whether we can just approximate the population related parameters or not, just to understand how it behaves and to find the relation between the sample related the statistics and population related parameters. So that is the reason. Okay, right. If some of the doubts are there, we'll see. Sigma square by n is okay, where here? The same sigma square n by is nothing but whenever we take the sample related, that is sample related mean, sample related variance, sampling distribution of mean and variance, then it comes to sigma square n, where sigma is nothing but variance of the population, n is the size of the sample. Right. Next is why sample follows normal distribution. I couldn't get it actually. No, it is actually. I can show some examples. If n is very large, then it follows normal distribution. That is the reason what we are using the standard normal distribution, irrespective of whether the population is normal or not. How large the sample need to be? Yeah, perfect answer. This is here in the previous slide I mentioned for large samples generally n greater than 30. n greater than 30 is considered as large sample. Otherwise, if that means n less than or equal to 30, then it is said to be small sample. How much larger that is, I think I need to mention. N greater than 30 is then we say the sample is a large sample. What is the use of the theorem? We'll see it actually. What is the use of the theorem? We'll see it. Many times we are going to use it actually. Many times we are going to use it. Suppose something like this, whether I had a example or not. And I'll try for an example. Here actually when we try to find out some mean related discussion which is related to sampling distribution, then there is no clue about it. Generally what happens is if the population follows normal distribution, right, whatever the data points are given, that is population. If it follows normal distribution, it actually makes sense whenever we select a sample, then also we assume that it follows normal distribution, right? That is a general notion, right? You have a population which follows normal distribution, already it is mentioned. Then whenever I select a sample, right, then obviously it follows normal distribution. But if there is no clue about the nature of the population, so we are not aware of whether it is fit to be a normal distribution or not, but still we want to do the sampling. And here it won't allow, if central limit theorem is not there, it won't allow us to use normal distribution. But the experiments what they have done it proved if the population is very large, not population, then the sample is large, that means n greater than 30, then irrespective of nature of the population it follows normal distribution. So that gives the freedom for us to go for this z is x minus mu by sigma, the regular expression what we use when we deal with normal distribution. Otherwise we can't use it and we can't do with it. Yeah, we'll continue here. We'll come back with further discussions. Now we are aware of the conversion which converts the normal distribution into standard normal distribution, that is x minus mu by sigma n. Right? Mu is the mean and sigma is the standard deviation. Suppose if we are dealing with problems related to sampling distributions, or if we are dealing with problems related to samples, then this is what we use. That is x instead of x, now we are dealing with the distribution, right? That is x bar, right? Therefore, x bar minus mu by, as discussed previously. Okay. As discussed previously, that sigma is nothing but sigma square by n. So x bar minus mu by the sigma square by n, but here we want x minus mu by sigma, that is only standard deviation, therefore square root of this. So this is actually we can use this because of central limit theorem. Because of central limit theorem only we are able to have this, which helps us to solve the problems when we go for sampling. Right. So clear? Yeah. Real time example I'll think and I'll try. Maybe while doing problems we use it actually. I hope that it's clear, right? What is central limit theorem? Because of central limit theorem, what is that we are able to get? Now this is one important outcome which helps us. Right. Next, coming to estimation. So estimation, if you remember the discussion what we had when we do sampling, right? What is the next step after sampling? What is the next step after sampling? Any guess? We did sampling, right? Then we'll have something, some outcome based on the sampling. So after this, what we do actually? we estimation, right? We do estimation, right? Suppose I want to find mean of the population. Then what I do, I select the sample, right? Then I find the mean of the sample, right? So that is X bar actually. From X bar, what we have to do is we want to estimate what is the mean of the population, right? So that is actually the process, right? We want to, again I repeat, we want to find mean of the entire population. So for that, what we are doing, we are selecting a sample and we'll do the analysis and we'll find the mean of the sample. So from the mean of the sample, we want to do is the estimation for the entire population, right? That is actually a simple example is, suppose a company is going to release a new type of motorcycle or car in the market, right? Right. So if you remember, whenever they release a new model, new car or motorbike, so generally we'll see what is the mileage they mention, right? So this model gives 75 kmpl. So how they arrive at, right? How they arrive at the 75 kmpl. So then actually what there is, maybe the model they are producing 3 lakhs or 4 lakhs products, the cars or whatever it is. So what they do, they take the samples randomly, they select some maybe 10, 20 or 30 bikes, and they will test all these vehicles under different conditions and they will list out the corresponding the mileages. Then they arrive at, so this is the average mileage, the sample mileage that we got from the sampling technique, right? So suppose they got it as X bar equal to 75. So they can't say that for the entire population it is going to be 75, right? They have to estimate it for the entire population. That is called as estimation. I hope that is clear, right? So population, then we'll take the sample, then we'll have the sample outcome. From the sample outcome, we will estimate it for the entire population. That is what we call as estimation. In general, estimation is of two types. One is point estimation, other one is interval estimation. But our interest is interval estimation. Now, in general, if you see, even in in regular applications also, whenever we estimate it, if you remember, we'll attain some percentage associated with, right. Simple example is, I will get A minus in this course. Suppose that is your claim or the estimation, right? Then immediately it's 99% chance that I will get it, 90% chance that I will get it, 50-50 chance that I will get it. Okay. So I get A grade or A minus grade is your estimation, your assumption, right? But always your assumption is associated with some percentage, right? So what is this percentage indicates? What is the percentage indicates? Any idea? Any guess? Any idea? Like what is the 90%? What we say? I'll get this 90% chance that I'll win the match, 99% chance that I'll get this, like this. So that is very much important, like, right? Suppose if I say 90%, then you say you are confident enough. Suppose if I say 50-50, right? Suppose if I say 40%, you are not having that confidence, right? So that 90% is nothing but the level of confidence that your estimation is going to be true. So that's why if you see here, why I am saying is this, whatever I have shown here is nothing but the level of significance as well as level of confidence. Right. Now, so what is this? Just to go, I'll just try to explain it. Go through it. Now, suppose with some assumption, that is with 90%, 99%. This is my 99%. 99% confidence I say that this is my estimation. So what about the 1% left over? It is you are not confident. 1% is in favor of you, that is I may not get this. So 99% is called as level of confidence. That 1% is called as level of significance. Now what I am assuming is, with 99% confidence, my Z lies between these limits. Actually, don't get scared of this. Just to understand the process, I am writing this. Then Z is nothing but x bar minus mu by sigma by root n, as discussed. Where x bar is mean of the sample, mu is mean of the population, sigma is standard deviation of the population, and n is size of the sample. Then if we do simple algebraic manipulation or simplification, that is multiplying both sides by sigma by root n, then it goes with this. Then we have x bar minus mu. X bar I will add on the both sides. Then we have mu. Then I will multiply throughout by minus. Then we will get this line. Don't get scared of this entire calculation. Just like that, you can see this. So from this you can understand what is this last expression gives. If you see, it is an interval for mu. What is mu? Mu is the mean of the population. We are calculating or estimating based on sample mean x bar. Okay. And sigma is, that is standard deviation, and n is size of the sample. Only Z alpha by 2 will be see what is this Z alpha by 2 in the other discussions. As of now, we think that something where we have the level of confidence, then we have some minus Z alpha by 2 and Z alpha by 2. So clear? What will be the alpha? We will see slowly. Alpha is nothing but 1% actually. That's 1 minus. Why it is 1 minus alpha? Actually, alpha is something which is that negative side. 1% is alpha actually. Then 1 minus 1% is 1 minus 1. That is suppose 0.1. That is 99% whatever we say, and 1% is there. Right? Then 1% is alpha. 99% is level of confidence. That is actual alpha actually. Alpha is 0.01. We'll see it. Actually, we are going to use it regularly. Which graph? This graph we'll see actually. Just what I request is just to understand with 99% confidence. With 99% confidence, I assume my estimation, that is Z, because x bar we can't estimate directly because we are working with standard normal distribution. Therefore, with 99% confidence, I assume that my estimation Z lies between minus Z alpha by 2 and plus Z alpha by 2. And this leftover portions are there, right? It is nothing but where my estimation fails, which is combining together is 1%. Yeah, I think some of you going further and making type 1 error type here. Yeah, perfectly. So here actually, don't be scared of. We are not going to use it, just to have an understanding of sampling outcome. Then what we do further. Just I took this, and we are not going to use it so regularly. Right? Don't be scared of this actually. That's why I don't want to skip it. I want to have the discussion so that you will understand the process of sampling followed by estimation. So here if you see two types of the same kind of expression. Here one Z alpha by 2 is there, another one is T alpha by 2. And why two expressions here? Whenever if we are doing the sampling and followed by estimation with respect to larger sample, then we use Z distribution. Large means again here n greater than 30 is large for us. Suppose if we are doing this estimation for small samples, then we use t distribution. We'll discuss this at an appropriate time. It is almost like normal distribution with a small change with respect to peakness of the curve. Otherwise, t distribution and these both are almost similar, right? So don't be scared of these derivations, formulas. No need to remember this also. Just for the sake of understanding sampling, sample outcome, then estimation. X bar is the sample outcome, and we want to estimate it mu, that is mean of the population. Then how to do it? When we do the estimation for the population, then the level of confidence comes into the picture. That is level of confidence or level of significance. With what confidence we are doing this estimation. So because of that, we get this all this Z alpha by 2. So try to grasp this much only. Don't be scared of by expressions. This I think now we'll see further. Whenever 95% will have Z alpha by 2 value as this 1.96. Whenever 99% the Z alpha by 2 becomes minus 2.575. If it is 90%, then it becomes 0.67, something like this. This continues. Actually, some of you are faster than me saying introducing the error. Now, this is one of the, after central limit theorem, whatever we are discussing today, after central limit theorem, this is one of the important points to be discussed. One is when we do estimation, particularly when we do the testing of hypothesis, whenever a claim is there, right? Whenever a claim is there, we will validate the claim with the help of sampling, then we will take the decision by it. So while doing so, these are the cases happens. Right? And second thing, when we do the sampling, when we do the estimation, when we test the hypothesis, there is a possibility that we commit errors. What are those errors? Two types of errors as mentioned. You see here. You may have a doubt what is H naught. H naught is nothing but our assumption or null hypothesis, what we call it. What does it mean? Suppose if I say my hypothesis is I had a fever. That is my hypothesis. I had the assumption or the feeling that I had a fever today. Then what are the two cases? We went to doctor. With this assumption, we went to doctor. And he also accepted, yes, after doing all the tests, he also accepts and say that, yes, you had a fever. That means, yeah, he has taken a right decision. So, what are the assumption that we had? Doctor also agreed and he accepted it. Next one, I went to meet the doctor. I had with the assumption that I had a fever. Then after seeing, but doctor simply rejected my assumption. But originally I had a fever. I had a fever. It is true, but doctor rejected. Right? This is one error. Right? He is there, but he is rejecting. And second case, H naught is false. My hypothesis is false. It is false, but he is accepting. Right? That is a wrong thing, right? So that is an error. Type 2 error. And it is false, and he is rejecting. It is false, and he is rejecting. That means perfect decision, correct decision. So these are the two types of errors that happen when we deal with testing of hypothesis. Now between these two, which one is prominent? Which one is important? Can you guess? To take any example of your choice, and which one is the error to be given importance when we deal with the testing of hypothesis kind of situation. Type 1 error, yes, it is true. Assumption is true, but rejection. Which one? Which one actually? Same as confusion matrix. Okay, right. Yeah. Which one is type 2 is important, critical? Okay, type 1, type 2 is important, right? Correction, correct decision. Correct decision is, if it is correct, then we need not think about it. Only our interest is error, right? So what are the errors happens when we do the estimation? We have to focus on this errors happening in the estimation, right? That's why our focus is on type 1 error or type 2 error. Okay. Type 1, both the answers came, type 1, type 2. Yeah, false positive, okay, right, right. Fourth one, right. Type 1 error is important actually. Not depends on the use case. It is something like uh, something like I tell. Suppose, for example, this I went to meet a doctor. I had some pain here. I had some pain here, and I assume that this is some problem with the heart, like heart attack kind of scenario. I went there, and it is true actually. It is true, but doctor assumed that it is some because of some gastric trouble kind of stuff. Then he rejected. No, no, nothing is there. Let's go out. So actually, this is an error. Like originally, there is a problem here. It is almost like a heart attack kind of scenario. But doctor says nothing is like that. Just it is a gastric trouble kind of problem. So take the rabbit and go. This is one scenario. Second one, some problem is there. You went there, whatever, and I assumption is I had some heart problem, maybe heart attack, right? I went there, but what doctor says is yes, you come here. Originally, it is not a heart related problem, but what he says is you come, join here, we go for bypass surgery. This is also error, right? So between these two errors, which one is critical? Both are critical, but importance is for what? Type 1, right? Type 1 is error is dangerous. Type 1 is dangerous. I saw this actually. I saw these two cases happen to my two of my relatives. Yeah. So one case, what happened is he had some problem, like what I mentioned. He had a problem at 6 o'clock. He went to a hospital, and doctor, after seeing him, is a very lean. He asked whether you have this habit, that habit. Then finally says nothing like that. Just it is a gastric trouble problem. Go and take this one or two medicines. So by tomorrow you'll have. That happened at 7 o'clock. At morning 2 o'clock again he had the same problem. Then he called some doctor. He said, no, it is a heart related problem. So the first doctor committed a method. So because of which the second time he had the heart stroke. It is a very dangerous error, right? Second one of my close relatives, she had some problem. She went to a doctor. He said, come on, immediately admit in the hospital. Then by within 2 to 3 hours, we have to perform the surgery. So meanwhile, they called one of their relatives and verified. He said, after listening to all this case, it is some problem with the gastric trouble. So which is actually H0 is false. My assumption is false, but doctor accepted it. So between these two, which one is dangerous for me? This is. That is the first case. If still second doctor also do the same type of error, then third, so everything goes in wrong direction. So that's why, even though both errors are important, but mostly our interest is in this type 1 error. So the probability of happening or committing the type 1 error is nothing but the alpha what we discussed. So previous slide 1 minus alpha what we discussed is this. Alpha is nothing but the probability of having type 1 error. So I hope that is clear. So what is then I think maybe in upper maybe later I think I can share one. So what is the significance of type 1 and type 2 both errors? Actually these two errors alpha and beta helps us to understand the power of the test. Maybe I think if I discuss, I think it becomes more deeper, right? Maybe I can share some thoughts related to this, right? Because whatever we do mostly it is related to type 1 error. By considering type 1 error, we proceed further. But type 2 error, that is probability of happening of type 2 error, that is beta, is also equally important. So to find out the power of the test which we use. So maybe that I think I can share some of the thoughts related. Okay. I think I hope that you will accept with what I say. Like what I say is type 1 error is important comparing with type 2 error. You can try to imagine some of these scenarios and understand whether type 1 error is important or type 2 error is important. Yeah, some good example again. A bug is not found when there is a bug. If you can articulate a situation related to this, a bug is there, but bug is there. Actually, it is true, but not able to identify it. On other one is reverse type. So bug is there, we are not able to identify. Bug is not there, but we say there is a bug. So these two types of scenarios, if you take and articulate, then you can understand. So correct decision, we are least bothered about correct decision. Bug is there, identified. Bug is not there, identified. So correct decision is not a problem with respect to us. So our focus is with respect to type 1 error and type 2 error. So I think we'll take 3 minutes break, then I'll continue with this.